Well, everyone, we have a real treat for you here today. Your speaker today is the actual author of ERC-2535, you know, the diamond proxy. So he knows everything about proxies, and he realized there was something missing in this landscape. And you've all had this opportunity now to learn about all these proxies before the diamond. And I think you'll find when you go through that, there were some gaps and that we needed something a bit more complete. Obviously, with that completeness comes a little bit more complexity. And that's why you're extremely fortunate today to be taught by the author himself, somebody who worked with contributors to be in a position to make an Ethereum proposal, an EIP. I believe it's an ERC as well, isn't it, Nick? I mean, you'll fill us in.
Yeah.
But you know, you're not going to be able to learn this from anybody better. So you know, really take this opportunity. There will be questions and answers. Try to be focused with that. Obviously, we've got a lot to get through. And so without further ado, I'm going to hand it over to Nick, and I want to give him a big round of applause, everyone.
Thank
Nick,
you.
the floor is yours.
All right, good. I have a question. Can people ask questions in the Google Meet messages and in Discord, either way?
They can type in the chat at any time, but they can also unmute themselves. Obviously, everybody knows they have to be sensible about that. Raise their hand, and once they've done that, I don't know if you can see that. There's a raise hands section. If you can't, we'll fill you in anyway, Nick. We're here. So yeah, anybody can unmute themselves and ask questions when you feel it's appropriate.
Okay, good. And I'm also watching the messages in the Google Meet. So like if someone has a question there. Okay. And also in Discord, I might check there. Okay, I'm going to start. So good. So I'm glad that many of you guys had a proxy session yesterday with Timodan. That's great. The first thing I'm going to cover actually is a little bit of basics on contract execution. So what happens when you make an external function call on a contract? I'll just kind of go through this kind of quickly, but it's good to know to understand how functions are identified in a smart contract, because that has a lot to do with diamonds. Okay, so when you make an external function call on a contract, there's data passed in the contract, and it's called call data. It's read-only, and the call data that's passed into a contract, it'll contain a function identifier, something that identifies, well, which function in the contract do we want to execute? And it also, so the call data will include this function identifier, which is called a function selector. So I'm going to use the word function selector a lot, and that just means a 4-byte value that identifies a particular function in a smart contract or any smart contract. All right, so the call data will have this function selector that identifies a function, and it's going to contain any arguments for the function that's going to be called, and that's the call data. Call data is passed into a contract when it's being executed. All right, so good. So, and that's what this slide is about. And then there's a question, well, how do you determine the function selector for a function? Like, how do you calculate that? And so how you do that is you take what is called a function signature, and a function signature is the name of a function, which you can see here is transfer, and then the types of its parameters. So we have address here and unsigned integer here, you know, for transferring some token. So that'd be like to where you are transferring the token and how much of a token. Okay, so and so what you do here to get the identifier is, you know, the next line here is you just do a cacac hash of that function signature, and then you just get the first 4 bytes of it, and it's just an arbitrary way Ethereum or Solidity, the programming, has decided to identify functions and contracts. That's how they calculate it. And so there's an example here where we're going to be sending 10 tokens to an address, and it shows an example of what call data looks like. It's the bytes, and then it's broken down here. The first 4 bytes is the function selector per transfer, and then we have the to address and the amount. So the whole purpose here is to get you to understand how functions are identified in contracts. They're identified with this 4-byte identifier, and this is a solidity convention. That's how it does it. Okay, so this next slide is really kind of about the same thing. I'm just going to concentrate kind of on the diagram here on the right. What happens when you make a function call on a contract? So you make an external call on a contract. All contracts, they start their execution at the beginning of their bytecode. It's, that's anytime you call a function on a contract, an external function, it's always just going to go to the top of its bytecode and execute from there. And the top of the bytecode, it's going to extract the function selector from the call data. So, call data is going to have as I keep saying, it's going to have the function selector and arguments. It's going to grab that function selector, and so a contract will typically have like a number of external functions defined in it. Maybe it has 10. So when your call data is going to say, well, which function out of those 10 do we actually want to execute in this contract? And so at the beginning of the bytecode, it's gonna do a search here. Okay, here's the selector from the call data, and now which function is this selector? It's going to do like if it's this selector, then we're going to jump to the bytecode for that function. If it's not, we're going to, it's going to check another selector, and it's going to check a linear search to find, well, which function do we want to call in this contract? And it's going to use that call data from that selector from call data, and it's just going to be comparing selectors till it finds the right selector, and then jump to the function code and execute it. It's going to decode the rest of the call data into arguments for that function and be executed. And so that's what you see here. So hope that has some idea of clarity what's happening when you make a external function call. You guys want to I just kind of want to make sure that I might be going too slow, I might be going too fast. Do you want to leave a message or give me a thumbs up if you're getting this, if you get what I'm saying? Okay, good. Bunch of thumbs up. Okay, good. If you have any kind of question about that, you can ask about it. My slides here are not like perfect in showing that on this aspect. It kind of gets better as we go. Okay. So another basic I want to cover, you should know something about delegate call. I'm just going to go over this one slide on it. So a regular external function call really kind of passes, you might say, the execution, like if you're at contract A and you do a external call to contract B, you might say that the execution context or execution environment switches from contract A to contract B, and you're in contract B, you're altering contract B state, you're doing things with contract B. That's a regular external function call. You're switching execution context. Delegate call is a different kind of call, external call, where it's more like you have contract A, and if it's going to do a delegate call on B, it's not going to switch execution context. No, it's more, the way to think of it is contract A is going to borrow some code from from contract B and say, well, give me your code for function blah, for whatever function 1. And so contract A gets that function from this other contract and then executes that function within its own execution context. It's going to modify contract A's state, and it's going to just run within contract A, even though the code came from contract B. So that's really what delegate call allows you to do. It allows one contract to borrow code from some other contract and execute it as if it's its own code. And so, it has address this and message sender these values. In a regular external call, these values always change. Address this is the currently executing contract, and message sender is, well, what's the address that's executing this? And so these always change when you do a regular external call. It switches, but in a delegate call, these stay the same because you're staying in the same execution context. So that's delegate call. Are people familiar with this? Can you give me some thumbs up or question like, okay, or okay, good. So you good. This is, all proxies use delegate call. Okay, good. I'm going to go on here. Okay, good. So now we're going to start getting the diamond contracts. I'm just going to read this. Diamond contracts often do not have any external functions defined in them. So there is no, like I talked about this thing where a contract does this linear search to find out, at the beginning of the bytecode, the linear search to find out what function are you trying to call. Well, a diamond typically has no external functions defined in it, so there's no solidity dispatcher. There's no logic to say, well, there's this built-in solidity logic. It's not there in a diamond because you typically don't define external functions in a diamond contract. What you do define is a special fallback function. The fallback function is what's executed when you don't find, like if the call data has a selector and you can't find that selector in the dispatch code, well, then that's when the fallback function gets executed if there is one. And so a diamond typically just has a fallback function. So, and the fallback function basically does its own dispatcher logic. So it says the diamond has a mapping from function selector to a contract address. So when you do an external call on a diamond, it gets the function selector from the call data, and it has a mapping from function selectors to contract addresses. And so it does a lookup. Okay, what's the contract address associated with this selector? And then it does a delegate call, and it passes the call data that was called on the diamond. The diamond was passed in some call data, and it takes that same call data, and just sends that call data. Well, uses that same call data with a delegate call. And so this allows a diamond to borrow a function from another contract, pass in the call data to that function, basically the arguments, if there are any arguments, that function, execute that function within the diamond's context, so modifying the diamond state, any storage variables or whatever is going to affect the diamond. So a diamond, which you'll see in the next slide though, these other proxies, they just have one implementation contract. Well, diamonds have multiple implementation contracts, but they're called faucets. And the idea that comes from the diamond industry, a faucet is a side of a diamond. Diamonds have many different sides, and each one is called a facet. I should say facet. Is the correct pronunciation, facet. All right. Good, so that's what that is. And actually this next slide says the same thing, it just says it a little bit differently because this is important. This is basic stuff on how a diamond works. And so this is just like the AI version that regurgitated what I said in the last slide. So an external call is made to a diamond. The fallback function reads a function selector from call data. The diamond looks up that selector in a mapping function selector to contract address. Once the contract address is found, the diamond executes delegate call to that contract using the same call data. The contracts that receive these delegate calls are called facets. A facet represents one side of the diamond. Okay, good. All right, so here's to illustrate it. Basically, you can see the external call coming in. The fallback executes. The fallback determines does a lookup function selector to facet. I'm going to use facet now. So then it does a delegate call to the facet, and the facet will have its own solidity dispatcher because the facet here is going to get the function select. So the facet here is going to get the function selector because the facet might have like 10 functions, and it has it's going to get the function selector from call data and determine which function needs to be called, and it will then execute that within the diamond. So the diamond storage is modified if it does that. So here's another diagram. Here's the diamond contract, and there's a map. You can see a mapping here. Bytes for the address, facets. So good. So this is an example of a mapping. And then what this mapping contains, you can see it's, okay, function 1, the function selector to that facet address, function 2 to that facet address, the same one, because facets, so this just really kind of illustrates it. And then you can see like facet A, if these functions here, function 1, function 2, if they modify storage variables, you can see that it's going to modify, say it modifies storage variables in a struct, it modifies them in the diamond. The facets themselves, they never modify their own storage. They only modify the storage of the diamond. So you could, in a way, you could say that they're stateless. We're just borrowing the code from them to execute by the diamond. I just say that a lot. Just want to make sure people get that. Good. What do I mean by dispatcher? So dispatcher, when a function is called, it's the code at the top of a contract that tries to find, well, which function are you calling? Because it says, because you have the function selector from call data, and it says, well, is this selector equal this selector in the contract? If no, okay, well then does this selector equal this selector, this different selector? Oh, it doesn't equal that. Okay, so then it checks the next. Does the call data selector equal this? Oh, it does equal it. Oh, now where is that function? That function is at some position in the bytecode, and then the bytecode has a instruction to go to that area of the bytecode and execute the function. That's the dispatcher. That's the Solidity's dispatcher. It determines which function is being called. Someone asked that. Okay. Good, you guys are asking questions, so that's good. Good, is it possible to have same function in different facet, and how is that handled? Yeah, so that's a good question. So when you have a diamond, or really any contract, you have, let's say faucet A has a transfer function, and faucet B also has a transfer function. It's the same function selector, the same name of the function, same types of the function, and so it has the same function selector. Well, there can only be one function selector. You can't have two function selectors that are the same in the diamond. So you can only have, so that's what happens. So typically, like the way diamonds are implemented is if you add a transfer function and then it looks like you're adding the same selector that's already in the diamond, well, if your upgrade function is to add, well, it's already there, so you can't add it. So typically you get an error. But if it's replace, if you're upgrade, you're saying you want to replace this function with this other one, they have the same selector. Okay, well now the new selector is going to point to a different faucet. So you replace. He's pointing to a different faucet now. That's even true in a regular Ethereum contract. You can't have the same function twice in the same Solidity contract, because then you can't have the same selector for two different functions. You can have two functions with the same name in a contract as long as they have different argument types, because that's fine. But you can't have the same name and same types for two different functions in any Ethereum contract, as well as diamonds. I hope that answers that question. Is there any chance of function selector collisions, like two different functions having the same selector? Well, yeah. I mean, the identifier is a 4-byte value, and so it's basically how many combinations of selectors can you have with 4 bytes, and it's like over 4 billion. So it's possible. So it's like one out of, it's very unlikely that you'll have two functions with different signatures that will hash to the same 4-byte value. It's like 1 in 4 billion chance. I mean, so I've never seen it. Like the implementations of diamonds I have, they prevent it, meaning that like, okay, you're adding transfer, Now you're adding some other name that hashes to the same thing, and you're trying to add. Well, again, okay, oh, or you're trying to add this selector, but it already exists in here, and it will revert. So like my diamond implementations, there's no worry about having different function names that hash the same selector. It's not an issue because it will revert if you try to do that. Yeah. You guys are asking questions. That's good. Some of these questions I might not totally understand. Like we can't use different implementations and then Doug a call to that, like we're maintaining storage in different instructions and proxy. There must be caution when naming function arguments to avoid it. No, you don't have to avoid selector classes. Well, the only thing you have to no, you don't. You don't have to avoid selector clashes because just the chances of two different functions hashing two different functions with different names hashing to the same 4-byte value. Anyway, it's not likely. All right. Okay. These questions are good. I'm going to continue a bit. Maybe some of these things will get answered. Maybe not. Oh, good. Are you getting it? Am I going too fast? A pull. I don't know how to do pulls on this thing, but it's just kind of a check if we're kind of going along okay. Okay, yeah, thumbs up. So, all right. Good. All right, we'll continue. But don't stop keeping asking questions. It gives me, maybe I won't answer you, but it'll give me an idea of, what kind of questions you have and where you're at and stuff like that. It's good. Okay, good. So now we're going to get into storage. It's kind of a complicated slide, but it's the point. This is about we're talking about facets, and you're defining contract storage in facets. We have a facet A, and we're just using Solidity's normal way to define a storage variable here, var A1, another storage variable var A2 in facet in the facet A. Now now remember, like these, if we're going to be reading or writing these, they're not actually going to be written to facet A, because when we do writes to reads or writes to storage in a facet, it's actually happening in the diamond because we're doing delegate call. So this isn't going to affect the facet storage. It's going to affect the diamond storage. And where is it going to be stored in the diamond? Well, the way Solidity works is when you define a storage variable, it stores it at the first spot in contract storage, slot 0. That's position 0 in contract storage, and the next one is going to be in slot 1. Okay, so that's fine. So if we add this facet A to a diamond and we read and write these variables, it's going to be read and written to slot 0 and slot 1 in the diamond. Okay, that's facet A. All right, so now let's go look at, we have another facet. We're going to have facet B. We're going to add this to the diamond, and it declares its own storage variables, var B1, var B2, and well, Solidity is going to store these at slot 0 and slot 1 in the diamond, because that's the way Solidity works. It just chooses the first position and the next position and so on. And so if we add both these facets, like if I call, we're going to have a collision here, because if I call a function on the diamond that's from facet A, it's going to write to slot 0, and then later on I call a function on the diamond that is from facet B, it's going to also write to the same position, slot 0 or slot 1, and for some other functions, for some other functionality, and we get our facets overwriting its data. So what this means, so we can't use Solidity's default storage declarations like this in contracts for facets. We can't do that. And this isn't unique to diamonds. Open Zeppelin, has this problem, and they had their own way of solving this, and then they abandoned that and switched to basically the same way that diamonds figured out how to manage this well. And so the solution is called diamond storage, and it's It's a standard. So by the way, it says ERC. There's like confusion. What's an EIP? What's an ERC? So all the Ethereum standards are EIPs. All the ERCs, all of them are all EIPs. And then there's different kinds of standards. And an ERC is a smart contract standard. And then there's like a core standard, which has to do with Ethereum clients. There's a informational standard. So like there's like this subcategory of standards, and ERC is a subcategory standard of EIP. So anyways, it's ERC, so it's a smart contract standard. So diamond storage. So here, the solution here for storage, this is what facets use to define storage and read and write storage, is we take a human readable string like my project.erc17, something descriptive of our storage, and we hash it. And this will hash it to some random, it'll give us a random number. And we use this random number as our storage location in the diamond's storage. So now we're no longer storing things at position 1, slot 2. No, now we're going to store it somewhere random. And so here we define a struct. Oops. And then when we define a function, get storage, that gets that struct at our random storage position. So we can now get our storage struct as a storage variable, and we can and now we can read and write that struct at our random position defined by our human readable string. And so then we have a couple functions that use it. We call get storage here, and it sets the registry limit. That's one way to do it. Here's another one. Here we define an actual storage variable S here, and then we can access the struct by S dot whatever that's in here. So this is called diamond storage, and this is a final ERC. This has been used for many years. You might have questions about security or clashes or whatever, but it's good. This has been used for 6 years. It's been in audits and things like that, and so it's good. How is diamond storage ERC 8040 different from namespace ERC 7201? Okay, that's a great question. I love that question. So originally, I think, I don't know, 2020 when I was doing diamond. So we were doing diamond storage about then, I think. And so diamond storage has been used for many years, and in diamond contracts, but it actually applies to proxy contracts. Proxy contracts have the same problems diamonds do with storage clashes between different implementation contracts. Because even like in a regular proxy, it only has one implementation. Well, if you're going to upgrade and use a different implementation, you can have storage problems. And so the diamond storage is good for any kind of proxy. So OpenZeppelin created their own standard that works the same basically of diamond storage, except for it's more complicated. They want to sort of, instead of using a human readable, they use a human readable string, but then they manipulate the result. And I looked at what they did. They actually published their standard first, and I looked at it, and I just thought that their additional manipulation was unneeded. It was just added complication. There's threads about that when they were published their standard. I disagreed with it basically. And so like theirs is fine too. It works. It's just this is just simpler to just do this, and there's nothing wrong with it. So it's been used for many years and been audited and so on. So it's basically their approach is similar to this, except for they, instead of attaching the string, then they do some subtraction and they do some additional manipulation. Why? Because they feel that, well, their kind of thing is, if, well, what if you didn't use a human readable string, but you use some other kind of value, and then that gets into security problems. If you're not using human readable string and you're using some like a hex value, or you're using something else, then you can get into security issues. But if you use a human readable string like this, then it's not going to be a security problem. So that's why, like this ERC 8042, it says, you got to use ASCII characters, and there's a, basically use ASCII characters, then you'll be fine. I mean, you should look at the, and it's, it's human readable, so you'd have to look at the EIP 8042. I think it contrasts, all goes into the difference between the other standard that OpenZeppelin did. What is a quick way to figure out if a contract uses not 8042? Well, I don't have a total answer on that, but there's a bit more to this. Like there's a special NAT spec comment that I don't show here. There's a NAT spec comment that says, oh, this is an 8042 struct, and so that comment can then be used by tools that process NAT spec comments to determine what kind of storage is being used there. Well, also you can just look like storage position, and does it have a get? You just have to look. Usually the string, like you'd have to kind of look. Does it have a get storage function? What is it doing? So that's one kind of how you can do it. So each faucet has its unique storage position. Could be, if you wanted to have every faucet to have its unique storage position, you could do that. But or you could have multiple faucets that use the same struct at the same location. So two or more faucets can actually access and read and write the same structs in the diamond's storage. So that's a design choice. If you want to have faucets reading and writing the same storage, same structs, you can do that or not do that. Yeah. I'm just going to check the Discord if anyone's asking. Discord, I don't see any questions there. That's fine. All right, I'm going to move on. Good. Keep the questions going. That's good. Okay, good. So facets can be reused. So here you have facet A. It's been deployed. It has its code. And you have diamond 1. It's been deployed. And facet A, its functions have been added to diamond 1. And and then diamond 2 is deployed, and it uses the same already deployed facet A. So actually, any number of diamonds can actually use the same deployed facet A. You don't have to deploy facet A over and over and over. Just deploy it one time and reuse it. And you can see facet A. It writes to the diamond's data A storage location, writes to data A storage location in diamond 1, and here's facet B. Same, writes to a different location in storage in the diamonds. Reads or writes. So yeah, so that's that. So facets can be reused, so that's very nice. All right, good. So now someone says facets basically seem like libraries that are deployed and not just inherited. Is that correct? Yes. Yeah, they're like on-chain libraries that you can reuse. That's right. And like some projects, a really smart thing is you create a project and you can actually create a registry of facets. So then, these are trusted facets for your project. And so then, your project or people, they can deploy these diamonds and they can just use the facets that are already deployed, that are registered in a registry. And I mean, that's what, it's just an example of reusing. A registry of faucets then can be reused by lots of diamonds, and that's something that works. Okay, good. So ERC-2535 diamonds has been the standard for like last 6 years for use for diamonds. So, and what does it provide? I just do a quick summary. It provides an upgrade function called diamond cut. The idea here is that, like in the real world, if you have a diamond, you to change the diamond, you can cut diamonds, and that will create a new facet, a new side. If you cut a diamond and you're changing it, it's kind of an analogy, not a perfect analogy, but it's analogy. So it's standardized an upgrade function. It's optional. It's standardized a diamond cut event for recording facets and functions add or replace removed in a diamond. So this is cool. So like when you deploy a diamond, the event says, well, these are all the facets used, all the functions used from the facets, and anytime you upgrade, you emit this event. And so you have an on-chain, an event, your events can then, record all your changes to a diamond over time. You think there might be a valid use case to have facet A as an upgradable proxy, like a diamond proxy forwarding to another proxy under facet or facet? Do I think so? I don't know. I haven't really used other proxies as facets. Maybe you could do something like that. Good. So we're breaking down a single smart contract and using this modular system for upgradability. Does it serve other purposes, basically? Yeah, it does. I'll get into that. So good. So standardizes introspection functions that return what facets and functions the diamond uses. So every diamond has these functions that you can call. It says, well, these are the facets the diamond uses and the functions that the diamond uses, and which functions using which facets. So you can query a diamond to see, well, what is its functionality? Where does it come from? So this standard is supported by Etherscan, BLOK Scout, Looper.dev, which is it's a website for diamonds, allows you to see diamonds and inspect them and other things like that. So yeah, and that's one of the main purposes of the standard, is to provide interoperability for tools. So you can have tools that upgrade diamonds, that can show what's in them using the events, can show what's in them using introspection functions. Things like you can use these, you can do testing tools for diamonds that use these things. Oops. All right. Yeah, I'll get into purposes for diamonds, but that's a little bit later. I usually come up with like, how is it useful? What's it used for, like in the beginning, but I didn't do that. At first, I'm just kind of letting you guys know what it is and how it works, and then we'll get into some things about like, what's it good for? Like, why would you want to use it? That kind of thing. Okay, so just to show a little bit, diamond upgrades. So this is just what this ERC-2535 defines an interface. What does the upgrade function look like? It's called diamond cut for upgrade. But you can see that it takes in an array of this facet cut, so each struct has the facet address and then the action. So from this facet, do you want to add functions? Do you want to remove them or upgrade them, or add them, replace them, or remove them? And then the function selectors, these are the functions you're adding or replacing or removing from the diamond. And so we go ahead and pass an array of those structs, and then there's this address init. So that's going to be in call data. So the idea here is that, like, maybe you're going to add some functions, but you want to initialize some data, as well as add some functions, but you want to initialize some things as well. And so what happens is this function will do a delegate call on init, passing in call data. So this really just allows your upgrade function to upgrade or modify its state. So this allows you to add functions, but also modify state that might go along with those functions you're adding. So that's what this is. Hopefully this makes some sense. The init and call data. You're going to call this contract with delegate call using call data. So call data will have like what function you want to call and any arguments that are in the init contract. This way to initialize your upgrade. It's optional. You can pass in a 0 to that. You can pass in 0 to those, and it won't be used. So if you just want to add functions, replace them, or remove them. Okay, so this is a diamond cut event. So this is the event that gets emitted anytime you add, replace, or remove functions in a diamond. It has the same shape as the upgrade function, because here you're using this array using these 3 arguments, and those are the 3 same arguments to the event, diamond cut event here. So it makes the code to emit this event very easy with the upgrade function, because you just pass in the same arguments. There's a couple of downsides to this event, which I later address, but is that it's pretty gas inefficient, because this facet cut has nested structs, and the structs have has an array in it, And it's also like if you want to create your own upgrade functions, it can be difficult because the shape of the data diamond cut, it wants it in this particular shape. And if you're making a custom upgrade function, that you have to still put it in the, maybe your custom upgrade functions have a different shape of its data and it doesn't match this shape. And so had some difficulty in creating custom upgrade functions, which you're also free to do. Like, you know, EIP20 doesn't mean, you know, it specifies a diamond and upgrade function, but you don't have to use that. That's just for tools, you know, interoperability. You could create your own upgrade functions that work differently if you wanted to. The only thing you really need to do is have the same diamond cut event so that, you know, you still maintain interoperability with event systems that work with diamonds. And you want to have the same introspection function so you maintain interoperability with tools and block explorers and stuff. Okay, here's the loop. Okay, so loop, diamond loop function. So in the diamond industry, a loop is a magnifying glass that is used to look at diamonds. You know, is this a good diamond? Let me look in my loop magnifying glass to see how good this diamond is. You know, is it that kind of thing. So anyways, but by loop we mean introspection. We mean, well, what does the diamond have? What functions does it have using what facets? And so here are the facets defined from, the introspection functions defined from ERC-2535. The first one, facets, it gets an array of this facet struct, and you know, so facet here is facet address and what function selectors from this facet are we using? Return that. So this facets here returns everything, all the facets and all its function selectors. So, and then we have some more. It gets more broken down. If you pass in a facet address, then it will say, well, what function selectors from that facet does the diamond use? And it returns function selectors. Yeah. Well, what are all the facet addresses used by that diamond? Returns that. Okay. And if you here we give a function selector to the diamond, it tells you which facet handles that. All right. Is this making sense? Is this any questions? Good. Okay. All right. If anyone's like lost or behind, just say so. It's okay too. But if I'm going too slow, good. Upgradability. Good. Yeah. So upgradability. Good. Yeah. So good. So this is the upgrade event diamond cut. So we want to tell the upgrade function. Well, basically we want to ask, well, what functions do we want to add to the diamond or replace or remove, and what facet addresses go with those functions. And so we have this facet cut struct, and the struct tells us, well, what's the facet address action are we adding, replace, remove, and what function selectors. So, and this is an array of those. And so the cool thing about this function is it allows you to add, remove, replace any number of function selectors from any number of facets in a single transaction, which is good because like when you're doing an upgrade, you want to have it be atomic. You want to have it all happen in a single transaction. If you do it over multiple transactions, you might have some kind of inconsistent state between, you know, maybe people are using your application while you're upgrading and you're getting some kind of inconsistent state thing because something happened in the middle of upgrades. Well, you can't have anything happen in the middle of an upgrade if the upgrade happens in a single transaction. So basically, if we're not upgrading, we do not need a diamond cut, right? The diamond cut is responsible for the upgrade only. That is true. Yeah, you could deploy what they call like an immutable diamond. It doesn't even have this function at all. It's just in like the constructor function of the diamond, you add the facets and the function selectors, and when you're deploying the diamond, you specify what does it have, and you don't specify an upgrade function. There's no upgrade function. It becomes an immutable diamond. You don't need you don't have to have an upgrade function at all. So you just need the upgrade function if you want to upgrade. In the future, do you want to be able to add functions, remove them, replace them? Then you need an upgrade function. So it deploys a new facet with whatever changes we make replacing the previous implementation. Well, it depends. Like let's say let's talk about that. So let's say you have a diamond and it has three facets: facet 1, facet 2, facet 3, and each facet provides some functionality to the diamond. Now you go, oh, you know, based on our experience with the users, we need a new function. Well, you just create a new facet, facet 4, with that function or functions, and you add that to the diamond. It doesn't replace, it doesn't affect anything else. It doesn't affect what's already in the diamond. You're just adding something, other more functions to it, and your existing functions and your existing functionality stays the same. So that you can incrementally develop your diamond here. Over time, you can just add more functionality over time, and you have this sort of systematic, you know, facet-based system that's consistent and that's not limited. Like you can add as many facets and functions over time as you want. It can be huge, it can be small. Now let's say you discover you have 3 facets and that are added to your diamond, and facet 2 there's a function that has a bug in it, and you go, oh, we really need to replace that function. Maybe that facet, maybe you have 5 functions from that facet, and there's only one function that has a bug. Well, there's different things you can do. You can do an upgrade here that just replaces that one function and doesn't touch anything else, just that one function that had a bug. Or since you go, well, you know, or if you want to like maintain some consistency, meaning like facet 2, there's a bug in one of its functions, and so you have a source code with it fixed, but you want your source code to match what's in the diamond. So you replace, you know, maybe facet 2 has 5 functions in the diamond, and so maybe you replace all 5 functions in the diamond with just because you want some, you know, you want your new facet that's replacing just to match. So there's some organizational reasons you might do things, but basically you can add, replace, remove things, and not have to affect other things. So I hope that answers some question. Who has the authority to make upgrade, Diamond Proxy or some other user? So yeah, so you know, and this is covered. You know, some of these covers are covered in the ERC-2535, but you want to make this diamond cut. You know, you want to use a modifier only. You know, only admin or something, or you need to have some authentication. You want to have the owner of the diamond that can only the owner of the diamond can call this function. The standard doesn't specify who can call this upgrade function, but you definitely don't want everyone to be able to call this upgrade function, because then any malicious person could call it. So you could have a DAO. You could have a multi-signature contract. Multi-sig contract can be the only thing that calls it. You can have whatever kind of authentication scheme you want, but you definitely want to protect that upgrade function somehow. Is it like upgrading a contract, but instead we do it with functions? Yeah, basically. ERC-2535 is function based. So, you know, you can add functions, replace them, remove them. If you replace them, you can replace only the ones you want to replace and leave the rest alone. You want to move one function from faucet A, one function from faucet C, one function from somewhere else. You can just remove just those functions. It's really the granularity is function on this. You know, some people like to think not at a function level. They like to think at a facet level. So if they're going to replace something from a facet, instead of replacing that one function, they'll replace the whole facet, all the functions from that facet, because they want to think at a facet level and not a function level. So there's a bit of convention here on this standard, meaning like you can work at it at a function level, or if by convention you can do things at a facet level, replacing. I want to replace facets and not functions. So it's that's up on this standard. That's up to you how you want to organize that. Some people might feel conceptually working at a facet level is a better level. That function level might be too fine-grained. But some people want to work at the function level. So that's how that is. Yeah, so after deploying the diamond, then you can then call the upgrade function to make upgrades. And typically when you deploy a diamond in the constructor function of the diamond, you add some functions and faucets. You know, you're going to add the introspection facet with its functions. You could add others, you know, and then once it's deployed, you can then use the upgrade function to add more stuff if you want to. Or when you deploy your diamond, you can just deploy everything in, you know, and that's it. And, you know, you don't even need an upgrade function if you want to be immutable. Yeah, so then it goes, well, how does a diamond know which function in the newly deployed faucet to interact with after the upgrade? Okay, well, that's a great question. So remember what I've talked about, that there's a mapping from selector to facet address. Because when you deploy diamonds and you add facets, what you're doing is you're manipulating this mapping from selector, function selector, to facet address, and you're just adding to this mapping more of these things. Okay, I need to move along here because we're going to run out of time. So when you upgrade, you're just changing that mapping. So if you're going to upgrade a function, it goes from selector to a facet, and then you upgrade that function. Now you're going to change that mapping to that selector to a different facet address. That's how you upgrade a function. Okay, let's move along here. So this is an example of either scan support for diamonds. It's, you know, on the left here is a list of facets that are in the diamond, and on the right here are some functions that exist in a particular facet. This call data verification. This is the Li-Fi diamond. That's a DeFi protocol. Motivations. So I got to move faster because we're running out of time. I have to pay attention to this. Okay. So some motivations here is through a single contract address, diamond provides functionality from multiple. Okay, we know this. So I'm just going to simplify. So with a diamond, you can have a lot of functionality at a single Ethereum address. So if you have user interfaces that want to work with your protocol, you can just give them one address instead of 5 or 6. And so it can simplify working with external things, external user interfaces, other contracts. Instead of, you know, having a protocol with 5 different contracts that to be interacted with, you just have one address. So it just, you know, you say other contracts, they only need to call your diamond and no other contract. It just simplifies that. So so when you're building a large smart contract system, if you don't use a diamond, then you'll have multiple different contracts calling each other, and their states. You have state in different contracts, and you have authentication going on, and so you have that. So the idea with a diamond is it actually provides a structured way to have a larger system. You know, it provides a way to organize your code, and it has it has organizational benefits. So that's a reason you'd want to use it. Good. It provides, you know, you can deploy immutable diamonds, but also provides this incremental development. I told you, you can deploy a protocol, and then over time, based on experience, user feedback, you can add more functionality to it in a consistent, systematic, organized way. So you can grow your application with your users. And at some point, you want your diamond to become immutable. You can also always remove your upgrade function, so it can be you know, you can be upgradable until you don't want it to be upgradable anymore. And so it still has that ability to be immutable in the future. More benefits, okay. I mean, you know, the famous one is you're building a smart contract and you hit the 24 kilobyte maximum contract size limit. So you can use a diamond, and that gets you around that problem. You have on-chain reusability with facets. Yeah, so there's other benefits I already mentioned there. Okay, so if we still have time, then we could do a break.
We definitely have time. So
okay,
take your time.
Good. Well, so you know, we can do a little breakout here of two questions here. What could you build with diamond contracts? What would make sense to build with, that you think? So let's do that.
Okay. Shall I set up a breakout room now then?
Yeah.
Okay. Leave it with me. So that was super nice, the breakout. Thank you for that, Nick.
Okay, great.
We'll hand it back to you.
All right, we'll continue. And I'm going to keep going until someone stops me, or until I finish. So, but here we go. Good. So now, after I got you guys using your imagination, here's this slide shows some actual things in the real world that has been used, and some of these things have been in production for some years going on. So like we have ZK Sync, they've got layer 2 functionality they got this Ethereum diamond that's been helping them doing all this various layer 2 stuff. I have the links here if you want to see them or something. So we have Li-Fi, which is a DeFi protocol. So build a diamond around bridging assets and transferring them and things like that. We got Avagachi, a DeFi NFT game. Uses diamonds, got tons of contract functionality, so it's useful to have a diamond for that. Trust Wallet has smart contract wallets. Towns protocol, decentralized real-time messaging on the blockchain. Stovebox, tokenization of real-world assets. Venus protocol, DeFi, lending and borrowing functionality. Yeah, Boson, decentralized commercial exchange of any asset or service between any agent, human, or AI. Okay, so there's some things, and I'm gonna move on. Oh, here's some resources, and we're not done. I still got a bunch more here, so I'm just gonna transition to the next part of this session. So, awesome diamond. So it has a bunch of links about things about diamonds. There's the actual standard for yeah, I mean, back in like, just so it says EIP, you might be wondering, like, why don't I say ERC? I should, here I say ERC. I mix them up. Back in 2000, I was using EIP for diamonds, and then later on became more standardized that you use ERC for smart contract standards. So sometimes you might say it as EIP. That's just because it's old. Good is a blog where there's a lot of good information about technical information about diamonds, ERC-25 diamonds, about implementing them. That's useful. Discord server for that. Okay. Okay, good. So I'm going to talk about, I don't know, some future. So, ERC-2535 is a final Ethereum standard. I think it became final in 2022, though been around for a couple of years, so it's been around. So more recently, I've been working on a new diamond standard called ERC-8153, and it's called facet-based diamonds, and it's really reviewing, seeing how things could be better with diamonds with a having experienced things over time and getting smarter and things like that. So it addresses some things. So addressed perceived complexity, like a lot of people say, oh, diamonds are complex, and I never really felt they were very complex. The only thing that's complex about them is that, well, with the proxy contract that has one implementation contract, you just have one implementation. With diamonds, you have multiple implementations. I mean, but that's not really that complicated to me. Like, you have multiple indicators. Anyway, so, but there's a perceived complexity about it. And like, there's a lot of articles that say this is the more complex standard and thing like that. So, and then now all the AI stuff on the internet says it's complex because there's so many blog articles saying that it's more complex. And it has some more complexity, it's true, but it's really how diamonds work basically are not that complex. I don't think so. I mean, that's just my opinion. I also know it really well. So anyway, but I kind of wanted to think about how can I make diamonds, this pattern, with a standard, how can I make it simpler to understand, simpler to use, simpler to deploy, because that would make it better. It seems like things were more simple and easier. So so I made it. That's one of the reasons I'm working on this new standard to simplify things. So then we have high gas costs for deploying diamonds. So when you deploy a diamond, you have to there's the gas cost for deploying the diamond contract. There's gas you have to pass in all of these facet addresses and the function selectors. It's call data. If you have a lot of facets, like diamonds can be big. That's one of the benefits of having a diamond. You can make something big. And so it'd be nice that if you can make something big that doesn't cost a lot. And right now, if you have like 50 or 100 facets with a bunch of functions that you want to add to a diamond, you want to deploy that, it's a lot of call data when you're deploying. Call data is expensive. Not only that, but like you have to store the function selectors. Typically, it's usually done in contract storage. It's like 20,000 gas, to store a selector. And anyway, and then you have to store, that mapping selector to facet address, but you also have to store selectors somewhere else in storage for the introspection functions. These functions that tell you what's in the diamond. They need to know what's in the diamond, so that data has to be stored somewhere, and you kind of have to store selectors twice in a diamond. You have to store it for that association from selector to facet, and then you have to store it again for introspection, and it's expensive. So there's got high gas costs for deploying diamonds. I don't know, expensive is relative. I mean, Ethereum, the gas costs have gone way down. So sometimes a lot of times deploying diamonds is not a problem. It's not a problem for a lot of protocols and things. You deploy it one time, it's not like runtime. Runtime, you want to be very cheap because it's going to be called thousands or hundreds or millions of times. So you want runtime gas efficiency is way more important than deployment, which is going to happen once. Or you might have upgrades, but they typically don't happen very often. But anyways, I still like it to be less expensive. I might be over optimizing about the expensive because it might not matter really for most projects, but maybe it does. Function selector management complexity. When you deploy a diamond, you have to know what facet addresses and which function selectors. And Hard Hat and Foundry, they don't help you with that. And there's the regular toolings, they don't help you with deploying diamonds. And so there's some ugly code you have to typically make, and and even for upgrades, you have to write your own scripts to get the selectors from like ABI files, from some Solidity files. There's this tooling that has to be done to deploy diamonds. So that's what I say here. Some common tooling does not natively manage diamond selectors. Developers rely on custom script or third-party libraries to handle diamond plumbing. Yeah, so maybe that's not so bad, but if it could be better, I think that would be better. So that's what this standard kind of addresses. Makes it simpler, reduces gas costs, and makes deploying diamonds, the function selector, facet management, all that easier, simpler. Okay, it also simplifies terminology. This is perceived complexity. Some people didn't like the terminology for diamonds, that the diamond cut, the loop. People are less familiar with that. So in this standard, I get rid of those terms and I use upgrade diamonds and I use introspection or inspect. That could make it easier. So good. So this new diamond standard, ERC-2535, facet-based diamonds. So as we know, ERC-2535 is function-based. Well, this standard, ERC-8153, really is facet-based. You add facets, you replace facets, you remove facets. Internally, it's still working at a function level, but exterior to someone deploying, upgrading, basically it's facet-based. So one of the things we do is we introduce an introspection function, export selectors, which every facet must implement. So we're actually adding an introspection on a facet. So a facet might have 5 functions in it, and now we're saying that every facet must have this function called export selectors that returns the function selectors of that facet. So that's what it's doing. So the facet self-describes what it can add to a diamond. It returns, well, this facet A can add these functions to a diamond from that's what it supports. And you have an example here. So every facet would have to implement a function like this, export selectors, and there's some nice syntax for this. You can, this is real code where you say that, the contract has a function called facet address. It has these functions. These are the names, and then you just specify the selector, and this is how this every contract will say what function selectors it has, and that it can be used to add to diamonds. And it's returned as a bytes array. And there's just this convenience syntax here where you just use bytes concat, and you can put whatever function selectors you want in there. Well, that the facet supports. And so the idea here is that when you go to deploy a diamond, all you have to do is give it an array of facet addresses. And so the diamond gets those facet addresses, and then, in the constructor function, it will call the export selectors on each facet to get the selectors from that facet. And so that when you deploy the diamond can get the selectors itself and do everything. So deploying, similar with upgrading, you're just working with facet addresses. You don't have to worry about selectors, because the selectors are defined in the facets themselves and exported from the facets themselves. Does this make sense? Oh, someone's asking, what is this? So, what is this? This dot facet address dot selector. So this contract where this function is defined in has a function called facet address, and this refers to the contract that we're in. So let's say this is contract A, then this refers to contract A. And then facet address refers to the function facet address that's defined in this function we're in. Like, I'm only showing this one function in our contract, and then dot selector is the 4-byte function selector, function identifier for this function facet address. Does this make it clear? So, and Solidity has this nice syntax for us to specify selectors of the functions in our contract. That's what this is. This is Solidity syntax for specifying the function selectors of our functions. Yeah, so how do you prevent adding the same selector multiple times to a diamond that uses export selectors? That's a great question. So yeah, let's say you have facet A that exports some selectors and facet B that exports some selectors, and both facets, they have some of the same selectors in them, same functions. So when the diamond goes, when you're deploying it or doing an upgrade, and you try to add these two facets with some of the same functions, when the diamond first adds, let's say it adds all the functions from facet A, and then when it goes to add the functions from facet B, it always does a check. When it's going to add the function from the facet, it always checks, well, is this already in the diamond? And because it's storing, it's storing the mapping from selector to facet. So if it always checks, okay, I'm going to add this selector to the diamond, but it first checks, well, is it already in the diamond? And if it is in the diamond, and the fact that we're trying to add, well, then it'll revert, and it'll actually issue a custom error that says you can't add, a function that already exists in the diamond. You can replace a function that exists in the diamond, but you're trying, in this case, when you're deploying, or then you're just adding. You're not replacing. So the diamond itself will detect if you try to add the same function from different facets, and it'll revert with the custom error to tell you why. If time permits, can you please deploy simple diamond proxy adding and removing a facet? No, sorry, not today, but I am going to get to deploying, and there is going to be stuff about that, not in this session, but I'll tell you where you'll be able to find that in the future. What if we don't want to include all the functions in a diamond for a specific facet? Well, that's a great question. So for ERC-8153 facet-based diamonds, it's facet-based. So if facet A has an export function, it exports like you might have facet A and it might have 10 functions, but your export selectors might only export 8 of them. I mean, I don't know why it would do that, but The diamond's only gonna work with whatever the export selectors does. But let's say facet A exports 8 functions and you don't want to add all 8 functions. Well, with this standard, it's too bad because it's facet based. It's not function based. So if you know, what I would say is if you have a facet, you don't want to add all the selectors, is you break the facet into 2 smaller facets. So you know, you break facet A into facet A and B, and that they have lesser amount of functions. And so I've been working with that, and that's exactly what I run into is like when this standard 8153, I tend to work with smaller facets for various reasons, but that's one of them is like, well, this diamond only needs these 2 functions, so let's make a facet with only these 2 functions. You know, tend to deal with smaller facets with this standard because it's facet based. Yeah, so the diamond still stores all the function selectors in storage. Yeah, it still does store it still has this map internally. It still has this mapping from selector to facet address. But as I said, the introspection function, you also need storage for the introspection functions. And for this standard, the storage for introspection functions is less because we're working at a facet level anyway, and the facets contain the selectors. It's actually, you store less. You don't have to store every selector for the faucets. You just have to store really 1 selector for each faucet. Anyways, it's cheaper. It's less. That's where one of the gas cost things. But you still have to. It's just cheaper. I mean, it gets into more complicated implementation. But all right. So 8153, it does define its own upgrade function. So here, instead of, you know, you just really, if you want to add facets, it's just an array of addresses. We're not dealing with selectors anymore. You can replace facets. You know, you have the struct, what's the old facet in the diamond and what's the new facet you want to replace the old with. And it will go ahead and remove all the old facet functions and replace them with all the new facet functions. There's some interesting things here of like, well, what if the new facet has some additional functions the old one didn't? Well, in that case, it'll just add those additional ones. And anyways, there's more information on exactly how this works, but it does work nicely, or it does work nicely. And then an array for removing facets, you just provide a list of facet addresses and it removes all the functions from those facets. Then you have delegate. So this is like after you add, replace, remove facets, maybe you want to change some of the state in your diamond. You want to initialize something for new facets. And so we can do a delegate call to an address using delegate call data. This is a way for you to do upgrade storage. So you can upgrade your facets, but you can also make changes to your storage by doing a delegate call. To another contract if you want to. And then we have bytes tag. This is kind of like a metadata thing, like a versioning thing. If you're doing an upgrade, maybe you want to call it something like upgrade 1 or upgrade 2, and metadata is just anything additional things that you want to, other metadata about your upgrade. If you want to have like a commit type message that's longer than 32 bytes. It's optional. You don't have to use these. And these just get emitted in an event. There's a special event, optional event in this standard where the tag and the metadata gets emitted. So you can attach metadata with your upgrade. That's all this is, optional stuff. And the delegate call here where it's optional. Actually, pretty much all these things are optional. You can use whatever you want here. You can add facets and do nothing else, or you can replace facets and do nothing else. You can basically do what you want here. These are all optional. The upgrade is different from the system upgrade we went over earlier, right? So yeah, this upgrade function is similar to the ERC-2535, their diamond cut. That's their upgrade. This is like the comparable thing. It's the same thing, except for this is facet based. So like we don't have any function select. Like if we look at the ERC-2535 upgrade function, you have to specify selectors for each facet, and we don't have to do that because the diamond can call export selectors on the facets to get selectors. It can get selectors on its own. It doesn't need our help for that. But yeah, this is just the upgrade function that's comparable to ERC-25's diamond cut function. And we use different terminology here because we're trying to simplify, make it seem less complicated. Yeah. Okay, so ERC-8153 facet-based on events. So it has different events. So when you add an event, we emit, if we add a new faucet to a diamond, well, we just emit the faucet added event. You know, if we're going to replace a faucet, well, we just emit that event. We remove a faucet, we just emit. So this is very simple events for adding, replacing, removing facets, so we can kind of track what's been added to a diamond. And we don't have function selectors in here because, again, like, you don't really need it, because if you added a facet, you go, well, what functions were added to the diamond from that facet? Well, you could just call the export selectors function on the facet to know what selectors were added to the diamond, because that's where the diamond gets any selectors, is by the export selectors introspection on the facets, if that makes sense. So this is also, because these are simple, it makes it easier to create your own custom upgrade functions. You know, because your own custom upgrade functions should use these events when you add, replace, but they're pretty simple events, so it's easy to make custom. That's not true with ERC's 2535. There's a particular shape of data for the diamond cut event, and it's, you know, it's harder to could be harder to do upgrade functions with that, because you have to make sure your data is the right shape for that event, whereas this has very simple shape. It's just addresses. Okay. So ERC 8153 also has introspection functions, and these are the same introspection function as ERC 2535. So, you know, this is the same functions. That it returns to you what are the facets the diamond has and what selectors from each facet are being used by the diamond. Same introspection, which should make diamonds that implement ERC 8153, it hopefully will make them compatible with Etherscan and other tooling that rely on ERC 25's introspection functions, because I'm pretty sure, I can't say 100%, but I'm pretty sure that Etherscan and other toolings mostly rely on these introspection functions for their functionality, for the BLOK Explorer. The BLOK Explorer can inspect the diamonds, allow you to call functions on diamonds using their support for diamonds, and so this diamonds will probably work with those, but I can't say for sure because I haven't tested well enough. All right, good. So here's a summary of what ERC 8153 faucet-based diamonds. This is a draft standard right now, so it's not final. It still could have some changes, but I don't think it'll change very much. But sometimes I say that and then it changes a lot. So, but I still don't think it's going to change much. So this is what it does. Yeah, simplifies terminology, optional upgrade function, simplified faucet-based events, reduces gas costs for deployment, specifies introspection function for faucets, eliminates off-chain function selector management, same introspection functions as ERC 2535. Okay, what are its benefits from this? Diamonds become less expensive to deploy. Function selectors no longer need to be gathered off-chain. Standard deployment tools can be used without special diamond support. So it makes it, you know, you can use Hard Hat or Foundry or other things, and it's just you don't have to worry about function selectors. It's just you don't have to worry about special tooling or scripts. It's just easier to deploy and upgrade diamonds. Yeah, also because it's, for whatever reason, it's facet based, the introspection, not that it matters that much, but the introspection functions are simpler. Like, you can understand them easier, or, you know, the introspection functions on the diamond, you know, what functions and selectors it has.
Nick, just a quick question to break that.
Yeah.
How long does it take for block scanners to update to a standard like this if it got, you know, a firm standard? How long does that take?
I have a sense, I don't know for sure because it's up to them, but I have a sense it doesn't take very long, because I reached out to like Etherscan already about this stuff, and they respond to me and they say, yeah, we'll, you know, we're gonna we'll send it to our you know, our team. So I do think Etherscan will support this standard out of the box.
Yeah.
I can't say that for sure, but I'm pretty sure it will, because, you know, I've asked Etherscan, like, they're a little bit shy of telling me exactly how they detect diamonds, because maybe for some security reasons they just don't want to tell outside people too many things. But I do like Block Scout has told me they depend upon the introspection function specifically, and I think that Etherscan is doing that too, but I can't say for sure. But I think they are.
I mean, for the cohort in particular, I mean, they really need to understand that it's vital that proxies are adopted by the block scanners as well, so that people can really be sure when they go to an address, which proxy is this, and to easily look at the different facets, functions that are available. So that's another thing that Nick has managed to do. He's managed to convince all of the block scanners, because when you're writing a standard, it doesn't end there. That standard needs to get adopted. And so Nick has obviously been pushing that hard. And Nick, we're obviously grateful for that. So
yeah, thank you. Yeah. So it's to be seen if Etherscan. I need to, you know, deploy some of these, and you know, Etherscan also has like different supports different blockchains, and it's probably implemented the same on different blockchains and stuff. But anyways, yeah, that's that. Okay, so ERC 8153 faucet-based diamonds implementation. So there is an implementation of this. It's in a smart contract library called Compose, which implements this. And that's actually my project, and I'm working on that project, compose.diamonds. And the purpose of this project is to provide smart contract infrastructure to make it easy to deploy ERC 8153 diamonds with any tooling across many blockchains. Provide a set of standard on-chain reusable faucets, as you know, ERC-20, ERC-721. Make it easier to get started building smart contract system protocols. So that's that. So part of the idea is like, well, what if like there was some small standard facets, you know, like for ERC-20 tokens and ERC-721 and like these other common things, like these facets deployed on Ethereum at a particular address, but they also deploy on many other blockchains at the same address. And so then they just become these reusable building blocks for common blockchain functionality. And I make them small, like for ERC-7221, it's not like one, in Compose, it's not one facet. It's actually a number of different facets. It's like there's facet for allowance, for allowing others to transfer tokens. There's a facet for that. There's a facet for transfer. There's a facet for the metadata, like what's the token symbol and what's the token name. Like each one has this facet because maybe you want your ERC-20 token to have, you know, some of the standard functionality, but you want a custom transfer function. And so that way you can use 3 of the standard facets for ERC-721, but then, you know, have your own custom for, anyway, so it allows you to use some, you know, standard stuff, but then for your custom stuff, you can make your own custom facet and still use the standard deployed stuff. So you can so it's kind of fine-grained right now in Compose. But they work together. Like you can if you want the other standard ERC-721 token, you can just deploy the standard faucets for that. I mean, not deploy them. They're already on chain. So you just tell when you deploy your diamond, you just give the addresses for the already on chain facets, and then the diamond will add the functions.
Sorry to interrupt again. I mean, are they multi-chain?
They aren't right now, but they plan to be, so that exactly. So these facets, they'll be deployed on Ethereum at a particular address, and then many other blockchains deployed at the same address. So they exist. Yeah. Okay. So that's the idea. It's not done yet, but that's the idea, and I have plans for that. This Compose.diamond. It's in development. It's not ready for production use. It's the future. This is what I'm working on to make a reality. So if you're, so I'm just saying what I'm working on. I have a question. EIP is for protocol changes, ERC for smart contract patterns? Yeah, kind of. I mean, all Ethereum smart contract standards, they are all EIPs. So EIP is for all the standards. Then ERC, so ERC 8185 is an EIP because all Ethereum standards are EIPs. But ERC says what kind of standard is it? And ERC is for smart contract standards. There's other kinds of Ethereum standards. There's like the core standards. Those are all EIP standards too, but they're core standards, meaning that they're for the Ethereum clients. And then there's some other types of standards as well. So I have a question. You said you are working on this new standard. How does one submit a new EIP for approval to become an ERC? So the answer to that is searching online and finding EIP 1. Because that's an EIP 1, which you can find searching, is an Ethereum standard that tells you what the process is for creating a new Ethereum standard. And it tells you what to do, but you just follow. When I make a new standard, I follow EIP 1. Then there's a GitHub repository for ERC standards and for EIPs. But if you go to that repository, they have a template stand, like a template for making a standard. And so I use the template. It kind of tells you what to do for each section of the standard. Yeah, and then kind of follow that process. There's some things that aren't really documented when you make a standard, like when you're making a standard, you don't have a number for it, and so you don't have so places where you need to put the ERC number, I just use XXX and so on. So until you get a number, and that number gets assigned by one of the Ethereum people that working on the standard, one of the Ethereum editors or one of the helpers for the Ethereum editors. Is there battle tested and audited implementation of ERC-2535 Diamond Proxy or some base contract? Yeah, let me pull that up. There is some. Here, I'm gonna get you a link. So yeah, there's some basically like reference implementations that for diamonds that are good, that have been audited before. And also, if you go to the Awesome Diamonds GitHub repo is a good place for resources like implementations and stuff. I'll get a link for that. So, yeah. Okay. Oh, yeah. So that's actually a session I have. I have a bonus slide if we had time, but it just kind of goes into details about how does ERC 8153 reduce deployment gas. And I don't know, that's kind of really kind of implementation detailed thing. I don't know how really important that is to talk about now, but there's a slide. It's basically with this you can write less to storage. You can use less storage slots using 8153 because you're working at a facet level, and the facets themselves are already storing the function selectors. And so all you have to do is call the export selectors on a facet to get its selectors. So really, that's my session. But if we want to have any questions, any additional questions, then we could do that now.
Okay, Habibli, go for your question.
So I was asking if if there are any protocol that have adopted the ERC-2535 that we could actually look at their implementation.
Say again if there's anything what?
If there's any protocol that has adopted the ERC-8153,
Oh yeah.
other than the 2535, yeah, nice. Could you please like give a link out?
If anyone has adopted specifically ERC 8153 is your question, not that's your question, right? This one, ERC.
No.
Yeah, sorry.
Yeah, I think
my question is, are there any protocol that has adopted it? That was my question.
Okay, so for ERC 8153, it hasn't been adopted yet from a project that I know of yet. It's very new. It's it's very new. I think it'll be better than other ERC 2535, but it's very new, so it hasn't been adopted yet. Yeah, I mean it's yeah, so it just hasn't been adopted yet. I mean, I think it'll be great. I think it'll be better than, but no. And as you saw earlier, that ERC 2535 has been adopted by a bunch of stuff. And this is just a short list. If you go to Awesome Diamonds, there's a whole long list of like over 100 projects that have used diamonds. But that list is not complete. That's outdated. But this is some of the more major projects that have been built with. These are ERC 25 diamonds, which is, yeah. All right. Are protocol teams often interested in engaging you in similar high profile on auditing their proxy diamond implementation specifically? What is the demand for such reviews in Web3? That's a good question. So I would get people reaching out to me earlier years, like well, 2020, 2021, 2022, maybe 2023. I don't know about 24, but for a few years, I as far as like work, people, yeah, they would just reach out and want me to work with them on diamonds stuff. They're doing diamonds, and so there was like work, or you might say work. I did I advise projects as an advisor for some projects because my time was limited. But I sort of dropped out of blockchain space for a couple of years, just doing other things, and so then I got back into it this year and working on this new standard. And no, I haven't really gotten much people reaching out for me to engaging me in security audits, and no, not in a while. But those few years, 2021, 22, 23, I did have people reaching out to do audits on diamonds and audits and stuff. And I was doing perfect abstractions. I had an audit company. I had people working for me, and I kind of planned with the Compose library that I'm working on is getting this more Compose.diamonds, getting it ready for, you might say, projects to use for their development, and hoping then I might do more security. Not so much me. I'm more interested in attracting talented Solidity developers who know diamonds that can work with me and my company, Perfect Abstractions, to do audits, to do smart contract implementations with diamonds, things like that, as a business. And so I wanted to attract and work with people with that. But this is still very, very, very new, and I haven't had much engagement with it yet. So that's that question. And there's a question on the Discord about the diamond storage and comparing to the Open Zeppelin's namespace storage, or ERC 7201, about like, is the Open Zeppelin one more secure than the diamond storage, is basically kind of the question. And the answer is that the diamond storage specifies that you need to use human readable strings using ASCII characters. And as long as you use ASCII characters, human readable strings, it's secure. There's no problem there. The standard for diamond storage goes 8042. It goes into the security specifics of that. But then it's secure. There's no problem. But like the Open Zeppelin one, if you're not going to use ASCII characters and human readable string, you use something else. Well, that's then I'd say the Open Zeppelin thing is more secure. There is possibility of, I mean, maybe there's some possibility of some accidental problem. I'd have to research it more, but for diamond storage, you're like I said, human readable strings using ASCII characters, you're safe. Can we get any docs or GitHub for ERC-8153? Yes. I'm going to give you a link. To compose diamonds. There's a document section in there. I'll give you the GitHub. All right. So here's my there's my GitHub link to the actual diamond, ERC-8153 diamonds implementation. In regards to the human readable string, is it going to be a random string? Well, I mean, it should be a string that describes your storage. So like if it's storage for an ERC-721 token, it should be like, or you should be like maybe your project name dot ERC-721. So it shouldn't be random. It should be like somehow describing what your storage is about using ASCII characters. To tell you the truth, I mean, I think that if you just use any ASCII characters, I don't know at the moment. I'd have to check because it's been a while. But I think if you use any ASCII characters, like even if they're random, it's still going to be secure. But I'm not 1,000% sure on that because I haven't checked that in a while. So that might be true. So I have to. It might be actually covered in the standard ERC-8153. But I know for sure that if you use some sensible human readable string, it doesn't even have to describe your storage. If you said, my friend Jane or something like that, it's still human readable. It's going to be secure. Why? Can I ask why ASCII character? Because the ASCII characters represent specific bytes, and those bytes do not hash to. Solidity has its standard storage mechanism where it stores things at slot 0, and slot 1, and slot 2, slot 3. And slot 1, slot 2, slot 3, those are 32-byte numbers with lots of zeros. And the ASCII characters, they are not, they just won't map to the Solidity storage that Solidity uses. So it just doesn't. So the ASCII characters are safe. That's my answer on that. But if you use like a bunch of zeros, like 0 bytes, there's no, then you might be storing something at slot 55 or something because you're using these 0 bytes. But ASCII characters have no 0 bytes in them. So anyways, it's along that lines. Yeah. Very much interested around the vulnerabilities of the implementation of diamonds. What should we look for? What are some of the pitfalls devs often miss? Do you have any tips around testing environments and setups and harnesses that we can use to test diamonds and simulate issues and fixes? And so I would say, like, well, the most, I don't know, the most easiest error to make is like having facets and just define storage variables using regular Solidity, not using diamond storage, but you just define your storage variables like a regular, and that's just like, and then they add their faucets to their diamonds, and nothing works. I mean, that's just the easiest thing to notice. Like they're saying, oh, nothing works. It's very easy to notice that. But it doesn't happen. If anyone knows about diamonds very much, they don't do that error. And vulnerabilities, these are just really pretty typical security things for smart contracts. Trying to think of what a gotcha is. There's some knowledge on upgrades. Like, let's say you have a facet A and it has functions, and you want to add addition. You have a struct, and you want to do an upgrade, and you want to add more data, like more variables to your struct. There's ways you can do upgrades and add more state variables to existing structs, and that has to be done correctly. And there's an article about that on my ERC-2535 Diamonds blog. So I've written articles about these things. So you have to follow certain rules, but probably the better idea is if you have a facet and you want to add more storage, is just create a different struct and store it somewhere else. I mean, that's another, an easy way to add storage things to your diamond. Just create new storage structs for it. But you can extend existing storage structs if you do that right. If you do that wrong, then you'll corrupt your storage. Yeah. Let's see. Oh yeah, I'd also say that because you have facets, one thing you can do is you can test them in isolation. Like, so you have a diamond, you have 10 facets. Well, you can write your tests separately for each facet. That's one thing you can do. You write unit tests for each facet separately. And and you can understand each facet as its own thing. And so that's kind of gonna be nice. And then I think it's also a good idea if you have a diamond to test the overall data, sort of testing the I don't know what you call it, testing, test everything together and separately. That's what I would do. Test all the facets individually and test them all together in a diamond.
Okay, guys. Very last question from somebody. The rest will move to Discord.
Okay.
Who's next? Okay, I had a quick question, Nick. You mentioned gas saving for 8153.
Yeah.
Have we seen any analytics on that yet? Comparative to deployment costs of a diamond?
I mean, somewhat. I mean, I've run some tests on events, different kinds of events, and so I know that the 8153 events will be less expensive. Will be less expensive than the diamond cut event, which is big and heavy. So as far as actual tests, that's one of the next things I need to do is do tests. But I know for sure that it's going to be less gas expensive to deploy.
Sure.
Yeah, but how much it will be? Well, you can kind of get a sense because the 25, there's some things you can think with, like the 2535. You have to store each selector, and a selector is 4 bytes, and a slot is 32 bytes. So you can fit 8 selectors in a slot, and a slot is like 20,000 gas. So
big saving there, yeah.
So that's the 2535. And for 8153, I figured out that you can store, you need 1 slot for introspection, and that's it. Like, you can have, doesn't matter how many facets or function selectors how many you have, you just have 1 extra slot for introspection.
Yeah.
So it's constant time and a small amount. So so there's that difference.
That's great. And guys, any other questions, please just put them on Discord, whatever they may be. Nick will be around. He will be able to answer you there directly. So Nick, on behalf of BLOK Capital DAO and all our builders, the entire community, everybody on Discord, I just want to extend our deepest gratitude, Nick, for taking the time to explain this standard to us, insights into the innovative approach, modular, upgradable smart contracts. You know, and as the founder of this great groundbreaking standard, really, you've really inspired us here today to think bigger about blockchain development, scalability. So, you know, once again, thank you so much for sharing your knowledge, your passion around this. It really means a lot to us. It really means a lot to the emerging builders in this room.
Thank you. Appreciate that. Thank you, everyone, for having me and asking questions and being interested. I appreciate it. That's great. Great to be here. Thank you, Sheetal.
No, it's a pleasure. Yeah. Guys, that's a wrap. I'm sure you super enjoyed it. Let's give him a big round of applause. You can open your mute if you like. It's really, you know, it's been amazing today.
Thank you, everyone.